Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to discuss using I versus J for the imaginary unit. So in this topic, we're just going to discuss exactly that, using I or J to represent the square root of negative 1. Now, mathematicians represent the complex unit as I. That is, the square root of negative 1 is defined as I. And this is likely related to the fact that it is the imaginary unit. Problem: in electrical engineering, I represents current. Complex numbers are critical to understanding and modeling alternating current. Consequently, in the 1800s, engineers adopted J to represent the imaginary unit, the square root of negative 1. Now, some mathematicians object to using J simply because it is not I. However, consider the following. Every mathematician accepts a construct called the Quaternions. Now, the Quaternions are almost a field, except they are not commutative. That is, if Z and W are Quaternions, Z times W may not equal W times Z. We'll see why. Now, the Quaternions have three imaginary units, I, J, and K, and these are unique and different from each other. However, they all have the property that in itself it is squared equaling negative 1. So I squared equals J squared equals K squared equals negative 1. Every Quaternion is a real linear combination of these four values, 1, I, J, and K. So for example, you might have 3.2 minus 4.5 times I plus 6.1 times J plus 9.7 times K. Now, for example, we can actually define the sum of two Quaternions. Here we have two Quaternions, Q and R, and suppose we add them together. Well, we would just add the real parts together. That is 3.2 plus 1.7. Then we would add the coefficients of I and multiply the result by I, add the coefficients of J, and add the coefficients of K. So the sum of these two Quaternions would be this Quaternion here. Multiplication, on the other hand, is more difficult. Suppose we define I times J is equal to K, J times K is equal to I, and K times I is equal to J. Then notice what happens if we multiply the first equation on the left by I. I times J is equal to, I squared, which is negative 1, so negative J. So that's equal to I times K. But wait a second, if we take a look at the last equation, or the third equation, K times I is equal to J, whereas I times K is equal to negative J. Similar, from the second equation, we get that J times I is equal to negative K, and from the third, K times J is equal to negative I. So the Quaternions are not commutative. Q times R is not equal to R times Q. Now, for Quaternions to work, we lose commutativity. So that's something you may not expect. So they are not a field, because remember, for a field, we require that for multiplication, Q times R must equal R times Q. But that's not true for Quaternions. Now, Quaternions were discovered around the same time as vectors. In fact, there was a big debate going on between the vectorialists and those supporting Quaternions. Which is the most appropriate way to model the real world? Well, given that we don't have courses on Quaternions anymore, and we do have courses on linear algebra, it seems vectors won out. So we're not covering Quaternions anymore in this course. Okay, so the quaternions are not commutative. However, it happens that if we pick out only those quaternions of the form alpha plus beta I plus 0 times j plus 0 times k, all of those numbers are a subset of the quaternions that, for all intents and purposes, behave just like a field. Similarly, if we take all quaternions of the form alpha plus 0 times I plus gamma times j plus 0 times k, this is a second subset that also behaves just like a field. Between these two subfields, they are, for all intents and purposes, equivalent. In fact, they're more than equivalent. And so if a mathematician complains about you using j, then you can just say, look, the complex numbers with I and the complex numbers with j are just two isometrically isomorphic subfields of the quaternions. And that's true. Now, interestingly enough, there still are applications of quaternions in graphics. For graphics, well, graphics are in 3 dimensions. So let's throw out the real part. Assume the real part is 0 and we just are left with some real number times I plus a real number gamma times j plus a real number delta times k. Well, what's interesting is that quaternion multiplication can be used to approximate rotations in 3 space where the quaternion, or the coordinate beta, gamma, delta is represented by this imaginary quaternion. Now, matrices as well, which we're going to see in this course, also allow us to define rotations, but these are subject to something called gimbal lock, something that you may see later, especially if you get into aeronautics. Interesting thing is, quaternions also allow us to deal with rotations, but they require less memory and less computation for the same result. All right, in this topic, you now understand that mathematicians use I and engineers use j. You know that there is no difference between these two usages. Just stay consistent. By the way, many programming languages allow you to choose your imaginary unit, so you can use either I or j. You know you can joke about isometries between subfields of the quaternions, and you are aware that quaternions can nevertheless be used in computer graphics. Here's the references, acknowledgements, the colophon, and a disclaimer. Cheers!